probably saying that about sorry. Sorry.
Okay. We're live. Beautiful. Okay. You might want to sit a little bit farther back. So, to anyone who just joined us, I have snacks, I have waters. Please take. They will go to waste. Morning, Safe. Yeah, I'm sorry about the table setup here, but hopefully everyone can see me. And if you can't, I'm live streaming this right now on my YouTube channel. Somebody shared it with the WhatsApp group chat, the link. So, yeah, it'll be there too. So, I have a 4-part agenda for our lesson today. This is the review for your final exam. Okay, I've heard your final exam is on Thursday.
Yes.
All right, so that gives you plenty of time. All right, I just want to preface this by saying if there's anything that seems mysterious to you or unfamiliar, do not worry, you have time to learn it. And I believe that you can all learn it, and I believe that you can answer all of the questions on the test. There's not a single question they'll give you that you cannot answer. But we're going to prepare well so we know how to answer all of them, okay? So, number 1 is going to be a review of the 3 kinds of reactions that you've learned since exam number 2. That is going to be alkynes, radicals, and organometallics. Number 2, 3, and 4, this time I'm going to do straight questions. We're not going to be doing content for most of this lesson. So 2 is going to be mechanism, 3 is going to be product prediction, and 4 is going to be synthesis. And those go up in terms of possible complexity, but actually they go down in terms of how tedious it is to answer. Showing a mechanism is a pretty long process. Predicting products should be pretty quick. Doing a synthesis, you have to write even less because all you need to do is put in the reactants. So hopefully that order makes a little bit of sense as we go along, but definitely give me feedback. Another thing I'd like to do, by the time we get to the end of any sort of problem type, please give me problems. If anything has really kept you up at night during your studies so far, I want to see it so that we can all solve it and all learn it together. Okay. One more thing I want to mention before we get going. When I was in Orgo 1, I made myself a synthetic toolbox. Now, I think I have enough of these for everyone here. I printed out 20 of them, and I'm sorry if I don't. I can send you the PDF if I don't have enough. But anyone who wants one of these, I'll start passing these around. This has every reaction in Orgo 1 written on one sheet of paper. So if you know every reaction on this sheet of paper, I mean, nothing can stop you, okay? But you need to know how to use them too. You need to know how to use them too. And often I need to refer to my own synthetic toolbox constantly to solve problems. So it's not just enough to know the reactions, but it's a very, very good foundation. All of these, with the exception of maybe 1 or 2, should be second nature to you. Okay. Okay, so we're going to spend 30 minutes per section. We're already a little bit into this section, actually, because Learning Center is open a little late, but we can do 15 minutes for these reactions. I think that's fine. Thank you. In case I need it. All right. So which one comes first? Alkynes, radicals, or organometallics? I think an alkyne. All right. So that's going to be our topic number 1, alkynes. Let's see if this marker is good. Let's see if this board is good. Okay. It'll work. And apologies in advance in the YouTube live if we are inverted. Yes, Risley, I will send the PDF. Okay. Yeah, if you could just monitor this, people are actually chatting. Okay, awesome. Alkyne reactions. So of the reactions that I just gave everyone on paper, the alkynes are there, and I'm going to show all of them, with the exception of one, which is the alkyne shift. I had that in my class. It was a pretty neat reaction where you can make an internal alkyne, a terminal alkyne, but I did not encounter that in your guys' notes. But if you're familiar with it, that's cool too. Okay, so there are 10 reactions of alkynes, 10. And overall, it's good to think of an alkyne. The way I think of it is an alkene with an extra pi bond along for the ride. Okay? So whatever you're going to do to this alkyne, there's going to be another pi bond. And that pi bond can either stick around in your product, or it could keep reacting during the reaction and form a product without any pi bond. But either way, the first step is going to be just like with the alkenes, except you have an extra pi bond along for the ride. Okay, so let's start with the reductions. These are the most straightforward because you don't need to know any of the mechanisms. You have an alkyne, and there are 3 kinds of reductions you can do. You can do H2 and palladium, nickel, or platinum, and this reduces it to an alkane. An alkane has saturated hydrocarbons. So this is CH3, CH3, and this is CH. So you added 2 hydrogens onto each carbon. If you do H2 and Lingler's, and if this was an internal alkyne, you would get a cis product. There's a mnemonic. Catalyst cis. If you use Lindlar's catalyst, you get a cis product. Okay? And now there's this other reaction. Sodium metal and liquid ammonia. Okay? Well, it doesn't say C for catalyst, so it must be not cis. And there's only one other option, which is trans. Okay? So, cis catalyst, not cis, trans. Hope that makes sense. All right. Another really neat reaction with alkynes is ozonolysis. Now, ozonolysis of alkenes, you made aldehydes. Ozonolysis with alkynes, you're going to make carboxylic acids or carbon dioxide, depending on where your alkyne is. So let's say we have a terminal alkyne just like this. You do ozonolysis O3, another one where you didn't have to know the mechanism. I didn't have to know the mechanism. If you do, learn that yourself because I don't know it. Can't teach it to you. All right? A good way to do an ozonolysis product, in my experience, is to go like this and put an O on either side. This is a trick that I learned from a YouTuber, Leia Forsai. So it's like a tic-tac-toe board. You have 1, 2, 3, 4 O's. So I'm going to have 4 O's in my product. Well, here I have 1, 2 carbons. So my product is going to be the 2-carbon long molecule with 2 O's, aka the carboxylic acid. And then you're going to have good old carbon dioxide. Okay? So these are the 2 products for this ozonolysis. Ozonolysis is a good thing to be on the lookout for when it comes to product prediction or synthesis problems, because you're going to see something like a ketone, an aldehyde, carboxylic acid in your products, and you didn't look at the chapter about carboxylic acids or aldehydes yet. So there's only one way that you could actually get there, and that's by ozonolysis. Okay, we'll talk about the aldehyde thing later. All right.
Does that mean water though? Or
Sorry.
would we have to write water? O3 in water?
As a second step.
Yeah.
Okay, so yeah, that's a good point. But actually have to be H3O plus. You protonate the carboxylic acid. I'm not exactly sure if that's always shown. I just write O3 and it's assumed that the products are there.
Does this only work for terminal alkyne?
No, it works for any alkyne. So any alkyne can be done like this. You're just going to draw 1, 2, 3, 4 O's on either side. Okay. And I'll do more questions at the end because I just need to sort of power through these reactions so you can get the problems. Okay, so here's the point at which it becomes important to mention that an alkyne is just an alkene with an extra pi bond along to the right, because we're going to do some hydration. H2SO4 and H2O. All right. When we did this with alkenes, we got alcohols. When we do it with alkynes, we also get alcohols, but it's a special kind of alcohol because that alcohol has a pi bond along for the ride. So we'll see the first product and then we'll look at the second product. All right, here's the first product. It is an alcohol, just like with the alkene reaction when you do acid catalyzed hydration, but you have this double bond along for the ride. You learned in class that this is actually a little bit unstable. We'll go through the mechanism when we do the mechanism problems, but this is called an ene-all. This for ene, that for all, and they tautomerize to become carbonyls, okay? So that makes your ketone. You never want your finished product to look something like that. It's a little bit ugly, and that should cue you off to the fact that that first intermediate is not your final product. Okay, but what if we want it to be either 1, no carbocation rearrangement, or 2, terminal carbonyl, which is known as an aldehyde? Well, we can do both of those by just changing the reactants. So number 1, we're going to do what I call Markovnikov mercury. So this is HgSO4 and H2SO4. This gives you the same exact product, except there's no carbocation rearrangement. And then, if you want it terminal, just like with the alkenes, you got to use something that has boron. Because as we saw with the alkene mechanism, you have your boron babysitter who comes to protect that less substituted spot for an oxygen to come in and attack there in the mechanism. So we're going to use, this time we're going to use a boron that has 2 alkyl groups, BH, and then we're going to do H2O2 and NaOH to finish you off. Okay? That's 1, that's 2. And that's going to give you your terminal carbonyl. Okay. The 8th reaction, hydrohalogenation. All right. So if doing HBr on an alkene gives you a haloalkane, doing HBr on an alkyne will give you a haloalkene. So it's the same thing, except you have an extra pi bond along to the right. Let's draw that. So you have your terminal alkyne, and I'll do it this way just to show the regiochemistry here. And you do 1 equivalent of HBr. Why are we talking equivalents here? Because you have an extra pi bond along to the right. That pi bond, it could react if you have 2 equivalents, or it could not react if you only have 1 equivalent, okay? 2 pi bonds, 2 equivalents possible to add. What if we just add 1? That's going to add only 1 halogen, only 1 hydrogen. So we get our Br here, and then what am I missing? Extra pi bond along for the ride, okay? That's all that you're dealing with an alkene. You got 2 pi bonds, one's just sort of hanging out. It's the it's riding shotgun. You know, it's there, it's real. But you know, it doesn't change anything fundamentally about what you know about the reactivity of these pi bond containing hydrocarbons. Okay, then do another 1 HBr, and I could have written 2 at the beginning just the same. And look at that, 2 BRs. And you added another hydrogen right there. Okay. Next, what if we just do this with halogens? Okay. So the same thing as with an alkene. Right? If we add Br2 here, then rather than a hydrogen on this carbon, we're going to get a Br. And then on this one, we're going to get additional BRs on both sides. Okay, and it's the same thing with 1 equivalent and then 2 equivalent of Br2. Okay, and then there is what I consider to be the most important reaction of alkynes and the one you're going to be using the most often in synthesis. It's not a reaction that has a very complicated mechanism. In fact, it's just an acid-base reaction, but you have to use a very specific base if you want this to work, okay? Because alkynes are not acids. They just happen to be able to be deprotonated if you use an incredibly strong base. So let's take his other alkyl chain off. I'm going to put my cation here, Na+. Now, what is the name of the base that can deprotonate a terminal alkyne? NaNH2. That's right. So you're going to be writing NaNH2 all over your test. All over your test, okay? Why? Because it makes this. The alkynide anion, okay? The perfect SN2 nucleophile. Okay? And then what did we just form? 1, 2. And then here is form a new carbon-carbon bond. Okay? So this is one of the few ways that you know how to form a new carbon-carbon bond. Truly revolutionary. Deprotonation of alkynes. Very important for you to know. Sodium amide. Sodium hydroxide, not going to do this. Sodium ethoxide, not going to do this. Sodium amide. That'll do it. All right? Super duper strong base. If you want to think of how strong that base really, I didn't even write it. If you want to think of how strong this base really is, what's the conjugate acid of amide anion? Ammonia. That's a base. Okay, so you're the conjugate base of already a base. Crazy basic. All right, that's what we need to do our terminal alkyne. All right, that's the 10 reactions of alkynes that I know.
Can I ask you a question?
Yeah.
That's the reduction of the alkyne?
Just deprotonating. Sorry?
That was a reduction?
That was the deprotonation.
Oh, deprotonation.
Okay. So you had a question?
Yeah, so when you did the terminal alkyne, the 3 carbon terminal alkyne with one equivalent HBr, the first bromine will add on Markovnikov, so the middle, the second carbon, and you added another equivalent of HBr and put it onto the anti-Markovnikov. Do they both? Why is one Markovnikov one not?
Well, think of where the. Oh, you're talking about the HBr?
Yeah, like shouldn't they both be on the same carbon, the bromines? Yeah.
Great point. So if you actually drew out the mechanism for this and saw that there was a Br and then a double bond here, and you have another HBr, well, where is that H going to go? Is it going to go here, where you have a secondary carbocation, or here, where you would have a primary carbocation? Definitely the secondary. Good catch. So here is your product of double HBRing a terminal alkyne. Okay, very good catch. When in doubt about a product like that, draw out the mechanism. Thank you for pointing that out.
Peroxide, put it on the ROR.
We'll get there.
Right?
Okay, so although this would not be the starting substrate for a radical reaction. Okay. Radicals and organometallics. There are 3 radical reactions, and there's something I really want to mention at the top here, which is that one of them is the only reaction that you know how to do on this here molecule. Okay? There is only one reaction that you know how to do on a totally saturated hydrocarbon to use it for something useful. Okay, these are the radical reactions. And I'll emphasize that there are only 3 of them. Okay, so number 1 is the one that we can do on any hydrocarbon. Okay, any straight chain hydrocarbon, we can do this. And it is the one reaction that you know how to do on a hydrocarbon like this. I emphasize because if you're ever stuck in a synthesis where you need to add something to a hydrocarbon, you need to make something out of nothing, you're going to use this reaction. It's going to be Br2 and light, which is denoted as HV, or peroxides, which is denoted as ROOR. Very important note here, do not use hydrogen peroxide because it doesn't really work that way. Hydrogen peroxide doesn't form the stable radicals that a alkyl peroxide will form. So ROOR, okay? That's the one that you want to have on this arrow. Okay, we have Br2, ROR, light, and there you go. A Br is installed there. These are just the reaction arrows.
ROOR could be like COOH, for example?
No.
No?
No. This is, okay, so that's a very good question. COOH is a little bit different from a peroxide because what we're looking for in a peroxide is a oxygen-oxygen bond. Okay, you don't usually see that in molecules. You don't usually see oxygen bound to oxygen, and that's because it's actually not a very stable bond, which is why we use it for radical reactions, right? These can undergo homolytic cleavage and become the respective radicals. That's a very weird thing to be happening. So it needs an unstable bond, which is something like an oxygen-oxygen bond, in order to happen. All right, so it's not COOH, you need an ROOR. You could combine these two ideas and make your peroxide something like this. Okay. That's MCPBA. So, yeah, MCPBA with an R group. MCPBA without an R group would be this, which is what you use to make peroxides, not peroxides, epoxides. So, yeah, interesting thing there. You can have many different kinds of peroxides. They're not all H2O2. H2O2. Yeah. Okay. So yeah, number one, radical reaction, radical halogenation. The only thing you know to do with a hydrocarbon, and do not use chlorine for this. We're not going to go into the reasons why with like the Hammond postulate and the energies, but it's very straightforward just for you guys to memorize. Use Br, not Cl, okay? Cl is not selective, Br is selective for reasons that you should definitely know. It's actually quite simple. The intermediate, the transition state rather, for Br2 halogenation is closer to the products than the transition state for Cl2 halogenation. Cl2 halogenation transition state is more like the reactants, which means it is not as close to the thing that has the radical on the carbon. So radical stability is not as big of a factor when it's closer to the reactants. But when it's closer to the products, radical stability is a much bigger factor, which is why Br adds there. But Google that and look into it. I'm not going to get into it. Okay. Second reaction. So we've done with hydrocarbons. The only hydrocarbon radical reaction is Br2 over HV or ROR. Okay. Now we're dealing with these guys. They're alkenes, and there's two of them. One is HBr and ROR. And one is N-butyl succinimide and light, or ROR. Okay, so I want to draw a very fine line here between the first radical reaction, which is the only reaction you know how to do on a hydrocarbon, and all of the other radical reactions, because this is the only one you do on a saturated hydrocarbon, okay? Br2 and light. After that, you're forgetting about Br2, forget about saturated hydrocarbons. Now we're dealing with alkenes. These are the starting substrates for these two reactions. You should never draw these reaction arrows coming from anything that is not an alkene. Okay? HBr, hydrobromic acid. Different molecule from Br2, okay? We're talking about a different molecule. We want to add an H and a Br across this double bond, not a single Br to a saturated hydrocarbon, okay? That's why we're using hydrobromic acid. I emphasize this so much because I used to get very confused about this when I was in your shoes, and I don't want you to be so confused because there's a really big difference between Br2 and HBr, okay? Very different molecules, different properties that you've learned throughout the semester. Now, turns out when you use HBr and ROR on an alkene, you get your first ever anti-Markovnikov addition of a Br to a double bond, okay? Isn't that great? When we use just HBr and nothing, we get the Markovnikov addition. Why? Because we have the carbocation intermediate. When you use HBr and ROR, you get the anti-Markovnikov. Beautiful. Okay. NBS and light or ROR. Now, N-butyl succinimide, not such a scary thing. Not such a scary thing. I'm not going to draw it, but if I did, it wouldn't send shivers down your spine. It's not crazy. But really, all you need to know is that NBS is a source of Br2. Now, why wouldn't we just throw Br2 in this reaction? Because we would get this. We would get this happening. We want a different thing happening. We want something where we don't use a lot of Br2, and we need just a little bit. And in order to get that little bit, we use N-butylsuccinimide, which has, or N-bromosuccinimide actually, which has the bromine somewhere. Don't fact check me on that name, because I'm not 100% sure. But yeah, okay. So this is going to add to what we call the allylic position. So you might have learned at some point that this is like an allylic unsaturated hydrocarbon. And so the allylic position is going to be the one carbon away from this double bond right here, or one bond away, I guess you could say, from the double bond. So your bromine is going to go right here, and that's a pretty cool product. Okay, pretty unique when it comes to synthesis. Okay, so the 1, 2, 3 radical reactions you got to know. That's it. All right. Similarly, there are 3 organometallic reactions to know. All right, we're doing alkenes, radicals, and organometallics. So we're on our last one, organometallics, before we get into problems. Okay. Okay, so there's 2 G's and an L. Okay, there's the Gilman, the Grignard, and the organolithium. I write them this way, not because nature put them this way. Actually, these are man-made reagents. This is an increasing order of reactivity. Okay, your organolithiums are going to be the most reactive. Your organocupric, okay, it's called organocupric because copper, the elemental symbol is Cu. So I guess like in some ancient time, chemists called this cupric. Don't worry about it. It's just another way to refer to something that you already know. It's the Gilman reagent, organocupric. Okay, so increasing order of reactivity. But first we need to know how to form them, and then we need to know how to use them. So how do you form the organocupric reagent? Well, we do need to first start actually with the organolithium reagent. That's a very straightforward reaction. So you start with your humble bromoalkane. Okay. And you do 2 equivalents of lithium. Okay, 2 Li. Right? And that's going to make 2 times this. Just going to show that. Okay, so this is actually the organolithium reagent. Okay, it's the same thing. The starting substrate for the Gilman preparation is the same as the finished product for the organolithium. So it's just that hydrocarbon with lithium there instead. But what if we want to make this less reactive than the organolithium? Because remember, organolithium is the most reactive. It'll immediately react, and we'll see how it reacts. But if we want to make it a little bit less reactive, we need to use another reagent, copper bromide, copper iodide, something like that. Copper plus a halide. I'm going to use copper bromide because I'm already with bromine here at the beginning. So we use QBr, and I'm going to draw the product of this, but we're also going to demystify that product. So do not be afraid of what I'm about to draw. Okay, it looks scary and it is weird and scary. I agree, but it's not that bad. Okay.
Somebody's asking, isn't there a pentane as well as the reagent for Gilman formation first step?
Thank you very much. Yeah, that's a solvent. We're about to see very soon why you do need to use pentane solvent. Okay, pentane, hydrocarbon. All right, we're not even polar at this point. It's not a polar aprotic solvent. It's not a polar protic solvent. It's a non-polar solvent. Okay, and there's a very good reason that we use that sort of solvent when we're doing organolithium preparation, because as I said before, it's the most reactive. That's why. Okay, so now we have 2 alkyl chains coming off of a copper and a lithium counterion. Okay. It's a sort of weird thing. Another way to draw this, which is how you probably should draw it, is this times 2 plus copper. I like to draw it this way because to me it makes a little bit more like visual sense. Either way is correct. You have a copper bound to two alkyl groups. And all right, that's the preparation of organolithium. Organocupric. All right, the Grignard reagent. This is going to be the one that you're going to be using the most often. And it's no coincidence that it happens to be middle in terms of reactivity. Okay, it's not the most reactive, it's not the least reactive. It's sort of right there in the middle. It's a sweet spot. Very simple preparation. You have bromine, add magnesium, and you're going to be doing this in the lab. If anyone's going to take Orgo 2, you're going to make the Grignard reagent. It takes a while. It's not as simple as drawing out the reaction arrow. Okay, MgBr here. All right, there we go. The organolithium, now very simple again. We just do Br and lithium and pentane. All right, you do need to write that pentane in there. It's one of the few reactions where they do specify a solvent. And that's sort of, I suppose, testing you on the concept of lithium being the strongest organometallic species. Okay. Now let's go bottom up for the reactions. With lithium and Grignard, it's the same. It's going to be epoxide opening. Questions to the room. Did we learn how to use the Grignard reagent and carbonyls?
Yeah.
Yes?
Like to open epoxides or what?
To open to carbonyls, like aldehydes and ketones. It's not usually taught.
I don't think
Okay.
so.
Forget about it. Epoxide opening. That's the way we're going to use these, okay? So there are many, many epoxides, okay? This is the most simple. It's oxyrain. But there are many other epoxides, okay? Don't be afraid of these epoxides. They're all very simple at the end of the day. It's two sp3 hybridized carbons bound to the same oxygen and also bound to each other, all right? The sp3 hybridization thing is important because you're going to get an inversion of stereochemistry at the carbon that you attack to open said epoxide. And you need to keep track of that stereochemistry, okay? So let's say we had a CH3 group here and an H group here. Now you've noticed we have a carbon and it is bound to four things. Chiral center, okay? So you have two options in terms of how you want to draw this, how you want to draw this chiral center, right? You could draw it with the wedges and dashes on our oxygen, or you could draw it with the wedges and dashes on the groups coming off the oxygen. I prefer to do the latter way because it sort of makes me think that the epoxide bond is in the plane of the board. So I would draw it like this, where you have a CH3, let's say it's going forward, and an H going back. Okay, here's our epoxide. Now, this is a chiral center, but the opening is actually just an SN2 reaction, it turns out. So when you take your organolithium or your Grignard, I would use the Grignard. Personal preference, okay? Personal preference, use the Grignard. It is going to do an SN2 attack on this. What's the leaving group? It's the oxygen. Usually we don't have oxygen as a leaving group, but we happen to be in what they call a highly basic environment. And in this case, you can have oxygen in a leaving group because things are so basic that an oxygen with a negative charge is nothing to really worry about, okay? So the arrow goes like this, your reagent goes like that, and then you get the epoxide opening, and then you have to protonate the product. We're going to be doing that in problems, so I don't want to get into a discussion about it now. All right, so that's for this. Now, Gilman, you can use this for some really cool stuff, okay? It might seem like your least favorite because it takes forever to prepare. You know, it's a real pain in the butt to do this, right? Where you do the lithium and the copper, and then it's like two alkyl groups. I don't like it either. I don't like it to this day, but you do have to use it because it is the softer organometallic reagent, okay? So the way we're going to use this is actually on vinyl halides. And the way it is going to work is that you add the reagent to the vinyl halide, and only one of those two alkyl groups actually adds in, and then you get a preservation of stereochemistry. So you attack right there, the bromine leaves, and then you get a preservation of the trans isomerism that you had to begin with, okay? So let's say it was this with two carbons. You get a trans product. That's pretty cool, in my opinion. And where did we see this final halide? Well, we add one equivalent of HBr to an alkyne.
Yes.
No.
Oh yeah, it's not. That's not involved.
Yeah. Okay. So you add it, and it retains the stereochemistry. And think of it as because Gilman is the softer reagent, it's going to make less change in the overall product. Okay. I did these in order of reactivity. Down here, we're dealing with lithium. That's hardcore organometallic. Okay. Up here, softer. We're not really flipping the chiral center. We're not changing stereochemistry. We're just putting a new group onto that vinyl halide. Okay, these are the organometallics. Now, I want to make a huge note before we get into the reactions of of anything. A huge note about organometallics. They are like ridiculously basic. Okay, so if you have any sort of reaction with a even slightly polar, even slightly acidic reagent, your organometallic compound is going to react with the proton before it reacts with any carbons, and you are not going to get a new carbon-carbon bond. I'll show you an example of that. So, say you had a vinyl alkyl halide, and you want to use an organocupric. Great. Well, say he puts this vinyl alkyl halide. Okay, and he asks you to draw the product of this reaction. Now, this is a great vinyl alkyl halide here. It's a juicy bromine leaving group, great carbon to attack there. Oh, retention of stereochemistry, sounds great. But that's an alcohol. Now, alcohols are not acids. They're not very acidic. But as we learned in acid and base, oxygen with a negative charge, not the worst thing in the world. So it does happen. It does get deprotonated. And that organocupric, organolithium, and Grignard reagent, they're all going to go for that proton before they go for that carbon. Okay? It just happens to be the case. My rule, anything as acidic or more acidic than water is going to be deprotonated by your organometallic compound. So a classic trick would be for him to put something like this on your test, plus an organometallic, and ask what the product of that reaction is. What happens if one of these picks up a hydrogen where the metal is, forms an alkane? So you have this plus water, and you add the hydrogen there, your product is ethane, okay? CH3, CH3. No addition, no new carbon-carbon bond.
You have a few questions.
Okay.
Do you want me to say them?
Yeah, I'll answer those while I'm cleaning up the board.
Do Gilmans react with allylic position if there is an alkene and no other leaving group?
No.
Okay. The next question is...
I don't think so. I've only ever seen it when there's a leaving group. Because it's sort of like an SN2 thing, like the leaving group leaves while you attack.
The solvent for Gilman that beta.
Sorry?
Is it not eta
The middle
for the Gilman and the Grignard?
one. What's on with the Grignard reagent?
The solvent is not eta.
I guess so, yeah. I'm not really focusing on solvents. I'm sorry. A good news for all of you, you're not going to have to specify solvents in Orgo 2 because, I mean, you could, like, imagine having to learn all the reactants and then all the solvents on top. It's like, you sort of understand at this point that when you have something that is going to pick up a proton, you need a very polar, a very non-polar and aprotic solvent. There's going to be a point at which you have to stop memorizing that, and I'm at that point. So you definitely check out the solvents. Me, I'm not going to tell them. Sorry, it's just not. It's not what I do anymore. I wish I remembered all the solvents. Yeah, ether, like DMSO is sometimes a solvent. Pentane, almost never see. This is the only time I've seen pentane as a solvent. Learn your solvents, know them. They are important. Sometimes they react. Solvolysis. Okay. Yes.
With the Grignard reaction, wouldn't you put the aerial of the MG on the other side of the epoxide? So it opens up at least substitute. There's a CH3 you wouldn't.
Yeah. This is just to illustrate the stereochemistry of it all. If you had a more substitute position here, so say these are both CH3s, you're going to open here. That's a very good point. Yeah. So I should have specified. The epoxide opening occurs at the more available carbon, the less sterically hindered carbon. Very good point. Yeah. epoxide opening, just like any SN2 reaction, is sterically sensitive. So you're going to get the reaction occurring at the less substituted carbon. Very important. I wanted to illustrate here that there's an inversion of stereochemistry. So you're going to have to assign RNS to this chiral center, flip it around when you do the attack, boom, product. Okay. If you have any questions while I'm cleaning up, now's the time. I'm going to start with mechanism questions.
Somebody asked if it's an SN2 reaction for the Grignard epoxide opening, would it attack at the least substituted carbon?
Oh yeah,
Yeah.
exactly. Yeah, that's what your peer asked. Yeah, I should have specified that. It's the least substituted carbon that you react at.
And then somebody else said, also, can you repeat that last point on what happens with molecule with alcohol and why it attacks a certain hydrogen?
Okay, so that was probably about the polar protic reactant thing. So if you have your 2x copper lithium Gilman reagent, and then you're asked to do this reaction. Okay, so just a quick analysis of this molecule. This oxygen is holding on to a proton presently. Okay, so we can do two sets of analysis of this. One is a vinyl halide, which is great for Gilman because Gilman attacks vinyl halides at the halide. You need a halide there. At the halide leaves, and you get a retention of the stereochemistry sister trends. Okay, great. But we do another analysis of this. We actually see some pretty good acid-base properties, right? I mean, my acronym for this is ARIO, atom, resonance, inductive effect, and orbital. Okay, so atom, boom, oxygen, electronegative, can stabilize a negative charge. Resonance, boom, double bond, stabilizes a negative charge. Inductive effect, oh my god, yes, stabilizes a negative charge. We have 3 hits for acid right here. Okay, and it doesn't even need to be that acidic, right? It could have been this. It could have been good old isopropyl alcohol you used to wipe down like public equipment, right? It could have been anything slightly acidic. Do an acid-base analysis on any molecule you're about to react with an organometallic compound because you want to make sure it is not at all acidic. That's going to grab that proton right here. The electrons go to our oxygen, and you make this hydrocarbon not synthetically useful. It's basically a dead end, but you will have to show this product. I swear he's going to put on a question where you have to show the hydrocarbon product because it's important just to note that they're so basic. It's an anion of carbon species. That's super basic, okay? And then you have Br here, you have this, and you have your negative oxygen, okay? I lied, there's no resonance. But imagine there was, that would make it more acidic, right? All right, that's the point about anything slightly protic. Oh, another thing with the Grignard reagent. If you're going to do an epoxide reaction and then an acid workup, you need to specify 1, 2. So let's do MgBr here. This is a Grignard reagent, middle reactivity. And we do with oxyrain, and we do it with water, or H3O. Let's actually write in an acid. I like to use H2SO4. Okay, that's a strong acid. You can use any HCl, HBr, HI. Okay, so this is our epoxide, and this is our water. Now, there's a big problem here because that's a strong acid and a Grignard reagent. If you do this reaction, you're going to get an explosion. Okay, if you do this reaction, you're going to get an epoxide opening with an acid workup. Okay, why? Because I've specified 1 and then 2. That basically means like flask 1, flask 2. It is so important that you keep these separate, or else you're going to have like some OSHA violation on your hands. Okay, Grignard is such a strong base. This is, I mean, come on, you learned in Gen Chem that this is a strong acid, right? So it's going to be a very energetically favorable reaction, aka explosion. This is the better way to do it. This is a product of that. reaction. Okay. But let's get into problems because these are the most important thing for organic chemistry is doing practice.
We have to know the mechanism for the reaction you just proved.
For epoxide opening, yes. So it's just an SN2 reaction. Hopefully. All right, I'm going to flip this whiteboard because this side is getting go. Hope I'm not hitting anyone. Okay, this is Jesus. It's even worse than the last side. All right, whatever. We're going to talk through. So the blue marker was actually pretty good last time. I think it can survive a less than ideal board. All right, we're on topic number 2, which is mechanisms. So this is mechanism problems. And it is the first type of problem that we are going to do today. All right. I'm going to start you off with an easy one. And I have all of these problems on a good notes document that I believe I can export and airdrop to you if you really desire. Okay, so this is an easy mechanism for reaction. I call it easy. Don't listen to me. It's easy for me. It doesn't have to be easy for you. You have plenty of time to learn this if you don't know it already. But I thought it was important to note because of the whole keto-enol tautomerization thing. If you don't like enols, that's too bad because they're going to show up in Orgo 2 again. Okay, you're going to have to get used to them. I don't like them either, but they'll be your friend. Trust me. And they'll be more interesting, actually, than they are here if you do like enols. All right, so you have an alkyne. You have H2SO4 and H2O. This is acid-catalyzed hydration of an alkyne. So it's going to be the same thing as with an alkene, except you have an extra pi bond along for the ride. So our first step is simply grabbing a proton from our acid. Now, my Orgo 2 professor likes us to show the entire Lewis structure of a strong acid, even if its only function is as a proton source. Mode. Okay. Yeah, so I don't know if your Orgo 2 professor is going to be that sadistic, but mine is, so I'm going to draw the whole strong acid, all right? Okay, so this alkyne, slightly nucleophilic, slightly basic, comes out here, grabs that proton right there, okay? That goes to the oxygen on the acid, and we have an intermediate here. Now, draw a double bond. It's along for the ride. And we have a new proton. Where's the proton going to go? It's going to go here or there. Is it going to go on the secondary carbon or the primary carbon? Yeah, the proton's going to go on the primary carbon because the carbocation is going to be on the secondary carbon. Okay, so primary carbon is where the proton's going to go. So I have a proton right here that I just took from my strong acid. And we have a positive charge here. Okay, and also I specified water, and I didn't do the 1-2, so it's all there at the same time. All right. So now we have water. Water comes in to save the day, acting as our base, attacking here. Why don't I draw the conjugate base, by the way, of that strong acid? SOH, O minus. Okay, you should fill in the electrons here too, but that's the conjugate base of our strong acid. Now, I'm going to leave this actually to be. I'm going to use water the rest of the time, water and H2O plus. That's personal preference. I don't like to show SO4H minus working as a base because it really doesn't. It really doesn't. That's why H2SO4 is a strong acid. So I'm just going to leave it here. Draw this if you have the strong acid. If you want to keep showing this being a base later on in the mechanism, you can. It's personal preference. Okay, I don't do that because I don't like it. Okay, that's personal preference. Okay, so now we have our double bond, and now we have our water that we added in. All right, now it's time to show something acting as a base, which is why I did that whole little tidbit about my SO4H minus, and I'm going to show water acting as that base. Okay, you have a million waters in solution. Think of how much you have in a mole, right? 6.022 times 10 to the 23rd. You have plenty of waters. You're at no loss for waters. Okay, now it is time to say hello to the friend, the enol. Okay, this is our enol product. So you'll notice here there's no charge on this product, and that might lead you to believe that's the final product, but no, because we learned about keto-enol tautomerization. So tautomerization is just a fancy word for transforming one constitutional isomer to another constitutional isomer. But you need to know how to do the mechanism for keto-enol tautomerization in basic and acidic conditions. This time it's going to be in acidic conditions because what we're shown is an alkyne with a strong acid and water. So if it's a strong acid, we're going to have acidic conditions. No negative charges, only positive charges, okay? So the first step that I would show is this. I'll draw my enol a little bit bigger so that everyone can know. This is your enol, all right? Very important. Oh, no, that is your ketone. Enol. All right, so my first step here is to grab a proton as I'm pushing these electrons down. So I push these electrons down, and since I have H3O plus, I can show that as the proton source. Right, and that double bond grabs the proton, and the electrons go down like that. That's the first step. Okay. From there, now I have something that sort of looks like a ketone, but has this hydrogen coming off here, oxygen with 3 bonds, positive. And now I have an H here, which means that this is no longer a double bond. Now it's satisfied, happy, the proton is there. But this is positively charged, so, well, we just formed a water. Water is a weak base. Water acts as a weak base here and grabs that proton. The electrons go down to the oxygen, and you have a ketone. Okay. Keto-enol tautomerization. And at the end, we're going to have H3O plus. Do draw up the Lewis structure of H3O. He's a stickler for that sort of thing. And it should be pretty straightforward because you grab a proton. Any questions about this mechanism?
Yeah.
Okay, yes.
Do we have to show the enol and the ketone in equilibrium or not?
I don't think it's necessary for mechanism. It's actually professor preference on that one, yeah. If he shows equilibrium arrows on every step of keto-enol tautomerization, then I guess show equilibrium arrows. But really, only one of those directions forms the product. The other one is negligible, right? This in solution is much less thermodynamically stable than this. So you're going to get all of this, especially when it's ketone. Especially when it's ketone. Okay. All right. It's mechanism problem number 1. So as you can see, it's the same exact mechanism as alkene hydration. Oh my god. Okay, I'm going to erase this side of the board another time. You would think it couldn't get worse after that other side. You'd be wrong. Our skeleton here.
Can the proton being used for the tautomerization come from the OH group instead of water?
Come from the OH group?
Yeah.
I guess like the top one.
I'm not exactly sure what they mean, but anything that doesn't form a negative charge is okay to show with keto-enol tautomerization. Like, yeah, you just want to make sure it's coming from some acid. It could have been H2SO4 that you reformed after attacking another proton from SO3H. So that was just a personal preference. I didn't show this working as the base, but you could if you really want to. This is the SO. Right, the whole point of H2SO4 being a strong acid is that this is a negligible base. But if you really wanted to, you could show in keto-enol tautomerization the enol reaching out. Well, no, this would be, it would already be in the protonated form. Let's take out that little pair of electrons, and you would have, yeah. So there is some universe in which this could happen, right? Your SO3H is the one grabbing the proton, and then you form your stable ketone product, and your H2SO4, you write the friendly strong acid we all know and love. But is that going to happen? Like, I guess not in reality, but mechanistically, it does make sense, right? I mean, acid and base, they're just two sides of the same coin. This could work as a base in some way, I guess. It's up to you. It's up to you what you want to show as a proton source. Okay.
And then someone said, can you quickly draw that reaction in basic conditions?
Oh, keto-enol tautomerization. Okay. Yeah, that's a good one. So another important mechanistic thing you're going to have to do sometimes is do that same tautomerization in basic conditions. All right, so here's our enol. Stable, positive, not positive, neutrally charged. But what if rather than H3O plus floating around, you had NaOH? It's actually even easier to show this in basic conditions. And what I would do, so you have Na plus and OH minus. I mean, you have two options. You could show first it being deprotonated, or you can protonate it first. I would protonate it first. So if you do NaOH and H2O, I guess you could have it this, go down, reach a proton. And then here, the thing that would deprotonate this intermediate would be a base rather than an acid, or water, rather. Okay, so that deprotonated there. One problem with this is that it shows positive charge in basic conditions. Another way to do this is to have a deprotonation first, which might actually be the more correct way. So you have NaOH come in, pick off this proton, the electrons swing down here, and then the electrons swing up here. I'm showing this electron movement, although you could do a different one where the electrons go right down to oxygen. But this is actually showing you something that you're going to have to know in Orgo 2. This is called an enolate anion. Okay, so if you just deprotonated this first, you'd get this, and then being pretty basic, an enolate would then grab a proton from water. Yeah, this might actually even be my preferred one, because here you don't have any positive charge. If you form the enolate, play around with these mechanisms and figure out which one the professor wants you to draw, because that's one you got to do on the test. Okay, I'm just sort of cavalier about it because I'm not doing keto-enol tautomerization right now, but this is important. This second one is important, okay, because this is an enolate. Anyone want to guess what might happen if you have this? That's carbon with a negative charge, right? Maybe you have a haloalkane here, carbon with a negative charge. Maybe a little SN2 reaction. Just a taste of things to come. Pretty cool. Pretty cool. Okay, so my second mechanism question is a little bit harder. But that's where the learning is done. Okay. So we're starting with acetylene, and we have acetic acid. And don't be afraid of this question because, or I guess don't feel bad if you're afraid of this question because I did too when I first saw it. And you're going to make this. Okay, and your only reagents are HGS. Let me draw that a little bit better. HGSO4 and H2SO4, and this is a mechanism question. All right. So there's two ways to ask this sort of question. I mean, you could just start with an alkyne rather, and have HgSO4 and H2SO4, and then you have to draw the mechanism for that reaction. That's something you should know, have locked and loaded. But sometimes it's going to be applied to an unfamiliar scenario in which the products are not maybe what you would expect. Okay, but in this case, we're going to have to go off of our instinct and a little bit of analysis. So we have acetic acid here, and our alkyne. Now, acetic acid is not terribly strong, and alkyne is not terribly strong either. So we're not going to get a protonation of the alkyne as the first step in this reaction, as we do usually with the acid catalyzed hydration of alkynes. Actually, with the mercury reaction of alkynes, you get attack of the mercury first. So the acetic acid doesn't change the first step of this mechanism, which is actually attack of the mercury. Okay, so ignore the acetic acid for now. You can attack that mercury. Okay, so when it turns out, just like with an alkene, when you attack something like mercury or boron, any of these funky reagents that we don't usually see, you get your bridge like that. Okay. If you're following along at home, this is problem 7.13 from Brown Organic Chemistry textbook. Okay, so this is actually the same exact arrow movement as you have with the normal oxymercuration, demercuration reaction with an alkyne. Don't be tripped up by this acetic acid thing that we just added on. In fact, why don't we just discuss really quickly what that might be doing in the mechanism, because you'd have to actually think this through if you got this question on a test. So check this out. This is a double bond. Okay. Carbon, CH2. This is actually CH. And then this is this carbonyl with oxygen, carboxylic acid ester sort of thingy. Okay. We ask ourselves, where did each of these parts of the molecule come from with our reactants? Right. These are our reactants. Acetylene. I keep calling it acetylene. It's just ethyne. Okay. The name could not be less relevant. Okay. The importance is its reactivity. It is a 2-carbon long alkyne. Okay. Alkyne. That's going to be where the alkyne goes. Okay. Just like sneak peek, that's going to be where the alkyne goes. Because what? Are you going to turn the alkyne into a carboxylic acid? You don't know how to do that. Well, you can use those analysis, but that's not a mechanism that you can draw. So this is a drawing mechanism question. So cross ozonolysis off the list. Okay. So that's going to be where our alkyne ends up. Well, what's going to make this part? The carboxylic acid. Okay. So at some point we need to add this carboxylic acid to the alkyne. All right. Now we did learn a reaction where you take your alkyne and you add water to it. Okay. And we had this enol, and then we did keto-enol tautomerization. Okay. So what if rather than the water, I just took this group instead? All right, that's all that's happening here. Actually, that's all that's happening here. It's as if you took HgSO4 and H2O, and instead of the H2O, you just added a lot of acetic acid. Okay, so that's going to be our nucleophile. That's going to be the thing that adds it. You sort of want to have that running in your head before you go forward with your mechanism. Now, the mechanism for the mercuration reaction with alkynes, very similar to the one with alkenes. The first step is the attack of this Lewis. Would it be Lewis base? It would be Lewis acid, right? Because it gets attacked. It receives a lone pair of electrons. Okay, so that's your Lewis acid, Hg, mercury, and you form your mercurium bridge. This is sort of a freaky one because we have a double bond down there, but it's the same as with the alkanes actually. Okay, so now we have acetate, acetic acid, right, working as a nucleophile. Now, we're not going to get into the philosophy of why acetic acid would work as a nucleophile. It usually doesn't. It really usually doesn't. But in this case, we've looked at our products and we've seen there's actually no other way to get there than acetic acid working as a nucleophile. So we have to show it, okay? They're showing us the products, not us, all right? So we're not going to question whether or not acetic acid can add to this alkyne. They're showing us it's added already in the product, so it has to happen, all right? So the most nucleophilic thing on this acetic acid turns out is a double bond. Who knew? Just like an alkene can react with its double bond, right? And in order to have this not turn all positive on us, we need to satisfy that with electrons. And then the product of that arrow pushing, let's give Mercury these electrons. Okay. And let's kick out SO4 at the same time, is going to be this. So our double bond. We have Mercury plus flying off here. And we have the bond between this oxygen. Wait, let me show that a little bit more clear. Here, double bond here, oxygen here, here. Positive charge on that oxygen. 3 bonds on an oxygen positive. Okay. So that's actually like the hardest part of this mechanism. Okay. We're actually basically done with the reaction here. All you need to notice is that the most important part of this molecule is the tiny little thing hanging out over here. Okay. That's the alkene that formed from your alkyne. It's just the same thing as oxymercuration of an alkyne, except it's acetate as the nucleophile and not water as you're used to, or an alcohol even. You can put an alcohol there too. Imagine this was just an alcohol. Well, then we put an alcohol there. Okay. What's the similarity between acetic acid and alcohol? They're not strong acids. Okay, so they're not going to bombard that alkyne with protons. Instead, they could act as a nucleophile. They could add it. Okay, so it happens. It's weird, but it happens. All right. This first thing I'm thinking, we got to deprotonate that, right? We have aqueous H2SO4. That means water is floating around here to save the day. Boom, like that. Okay, so we're actually, if you redraw this, we're almost at our products, right? Because we have double bond here, methyl group hanging off there, the oxygen, and then your alkene, and then your mercury. Now, mercury removal is not something that you really learn the mechanism of. You used NaBH4 for it in the alkene reaction, but this time we're actually just using water because NaBH4 was not specified in the reactants. So you were given the reactants. Okay, so there we go. Acetic acid here, oxygen, and mercury. Oh, not mercury. Not mercury. That's toxic. That's instant death. This is a product. This is a product. Okay, so there you go. Boom. Now, the first step to solving this problem, if you were just dumbfounded by it on a test, which I would be too, it's a weird problem, is just to realize that there's something in your products that came from something in your reactants, okay? This has both elements of the reactants in it. So if you were asked, for example, like a synthesis question, where you actually had to fill in what happens in between here, you would have to start asking yourself, well, what possibly could make these two things add together, okay? What could do that? So one thing would be HgSO4.
I mean, we know that because of the ketone.
Well, this ketone actually is there because of this guy. Yeah. So yeah, you want to look at the product, sort of think of where they came from, and here they came from the reactants, and they always do. The products always do come from the reactants, right? Go figure. Okay, so I'm going to erase this now. Any questions from the chat?
Yeah, somebody said, how did Hg dissociate?
I don't know. Do you know? Look it up. Hg dissociates by like mysterious means in this class. In alkenes, we used NaBH4. Here we used H2O because that's all we had specified. I don't really know. I know you need some sort of reducing agent, and I guess water was sufficient for that purpose here.
And then somebody else said, why wouldn't one of the lone pairs near the acidic proton of the carboxylic acid attack the mercurium bridge?
Yeah, that's a very good question. So here we have our acetic acid. Okay, so why wouldn't that lone pair reach out? Why wouldn't that lone pair reach out? Why would it be this? Okay, yeah.
Well, because of resonance?
Yeah, basically it's because of resonance. I mean, you also need to think about the products here. I mean, you could actually show this one reaching out and attacking that mercurium bridge instead. I think you would get points for that answer. But this actually just makes the product a lot easier to draw because here, okay, so let's just like entertain that idea. You have your mercury here. Okay. And then you have your nucleophile. You could do that, but just notice that here you would be forming this instead. Okay, and then to me that poses problems because I don't know how to get that oxygen to be negative now. I mean, you could, I guess, push that arrow there, that one up there, have a double bond here now with the H, and then this, and then that. But that's actually the same exact thing as we had before, right? If we just attack with this double bond instead, we go right there, okay? No shortcuts. And you also have this guy moving its electrons up there. Okay, so that's just a quirk of the mechanism. Actually, you could have it be that one. You don't really need to think too hard about why certain parts of acetic acid may be more or less nucleophilic in this circumstance. Okay. Let's move on to some product prediction questions. Okay, so one type of question is going to be the mechanisms. Those, I mean, you have certain mechanisms in your brain, or you will by Thursday at least, and you know those. They're second nature to you, and you'll have to either one, draw out the mechanism straight, like if I had just had the alkene and no acetic acid, or you'll have to think a little bit and apply that mechanism to a different reaction than you've seen before. But the chemistry is all the same, right? Attacking mercury, removing mercury, adding in a nucleophile, it's all the same chemistry, okay? But it's the mechanisms are in your head. They're in this folder there that you're going to reach from during the test. So in order to learn the mechanisms, what I would recommend you doing is what I did in the class to learn the mechanisms. I'm mentioning this because we're going to move on to mechanism questions. Take a blank sheet of paper, try to draw it out yourself. If you get stuck at any step, just go back to your notes, see what the mechanism is, and correct your mistakes. Okay? If you keep doing that with these mechanisms, you will learn them, you will memorize them, and they might even start to make intuitive sense once you realize that it's all just acid-base reactions. These are all acid-base reactions, except for the radicals. That mechanism stuff you're gonna have to learn on your own. It's kind of a pain in the butt, but that also has a certain logic to it, right? You have homolytic cleavage, you have addition of one radical to the other radical. You have certain trends that are going to start reinforcing themselves. My advice, pull them from your brain, okay? That's what you're gonna have to do on the test. That's what you're gonna do while you're studying. Take them from absolutely nothing. Blank sheet of paper, draw out the mechanism from nothing, okay? Because that's how well you have to know these mechanisms. Then you'll be able to start doing a little bit extra thinking, apply them to a weird example like that. The other sort of question you might have to do is product prediction, okay? So we're going to do an easy product prediction first, all right? Now, these are the ones where they give you a starting substrate and they give you a reaction arrow with a bunch of reagents, and then you got to fill in that product. And boy, oh boy, do they mess me up, even today, even in Orgo 2. Because what you can do is just, oh, boom, I know the reaction, I know the product, but you just got to think a little bit, okay? You just got to make sure you're not missing anything when you draw out that product, because there's usually one product that they want you to draw to get the problem wrong, and then there's the other product that's a little bit different, but is actually the right answer. Okay. Sort of long-winded introduction there. Right. Okay, why don't we try this one? Just draw out the product of those reaction arrows. if you get stuck up, this synthetic toolbox should have all of these on it somewhere. Draw your own, by the way. That's a good way also to learn product prediction pretty well. You know, half of me making this toolbox was just an exercise to help myself study. Okay, beautiful. I see at least one person has it. Yeah. So first step, Lindlar's catalyst. You could have just as well said Na dot, like sodium metal plus NH3 liquid. Same thing. Why? Because these are two hydrogens. There's no cis-trans isomerism here. You don't have to worry about cis equals catalyst, trans equals the thing that's not catalyst. It's fine. Okay. So you're going to make first, number one is going to be an alkene. So with these product prediction things, you're going to have to show every intermediate. And here your first intermediate, same thing, except an alkene, double bond. What do we do with an alkene? With radicals, we have two options. One, we could do anti-Markov-Makov HBr addition. Two, we could do allylic bromination using N-bromosuccinimide. Okay? And that's what they showed here. Allylic bromination with N-bromosuccinimide and light. Okay? So there's the allylic position. Mark it off. There's only one allylic position here. Usually these problems there really should only be one because you don't have the tools to really suss out why one would be brominated and not the other. Okay, so here we have our alkene still here, and we have our bromine still here. Okay, so the product, after all that, is this bromoalkene. Okay, let's take it up a notch. All right, so we have ethene is our starting material, 2 carbon long alkene, the most simple alkene you know how to draw. And then our first reactant is HBr, hydroboric acid. Our second reaction is magnesium and ether, right? I wrote the solvent, ether solvent. Ether isn't reacting, but the magnesium might be doing something you've learned. 3 is oxyrane, so the most simple epoxide. And then 4 is HCl and H2O. Okay, so try to solve this real quick. All right, so I'm going to start with the HBr. Okay, so let's do answers down here. Let's do them in brown. Hopefully no one writes in brown on their test. Okay, so 1 HBr, what does that do to an alkene? Hydroboration, all right? So we're just turning that alkene into our friend ethyl bromide, or whatever the name of this is. Okay, so 2, magnesium with ether solvent. One of the organometallic reagents that forms, it's the middle one. Grignard, yeah, Grignard reagent, okay? So very simple, you don't need to show any mechanism. Actually, this isn't a mechanism question, so you don't have to show that anyway. But when you have bromine and magnesium here, they get together and form NGBr, okay? Anionic carbon species, Grignard reagent, middle reactivity in organometallics. Okay, so what's the one reaction you know how to do with the Grignard? Epoxide opening. There's an epoxide right there, and there's no sort of protic thing to ruin the Grignard, okay? So it's in its own step. Throw in a bunch of oxyranes, that's it, all right? So my 3, at this point, even though it's simple, I just want to emphasize this. I'm going to count carbons, okay? And there's nothing wrong with counting carbons, okay? There's nothing embarrassing about doing that. It's actually common practice. You're going to be using it for all of Orgo 2 as well. Count carbons. Do not want to defy the law of conservation of matter, okay? 1, 2, 3, 4, okay? I know the reaction. I know the number of carbons. There's not even that many carbons here, but just for the principle of it, I just want to show you me counting carbons. Nothing to be embarrassed about. 1, 2, 3, 4. And then our O minus. Okay. There was nothing here to ruin the Grignard. There was nothing here to protonate your oxygen. O minus. That is an intermediate, not a product. Okay. Easy way for losing points on the test is not showing this as O minus here. All right. You want to sort of run the mechanism in your head and think to yourself, well, if I have this epoxide opened and I don't have any protic thing to ruin the Grignard, I'm going to need to show that as an alkoxide first. Okay. Number 4, HCl and H2O. This is what they call an acid workup. Okay. Really, it's the first reaction that you ever learned in organic chemistry, which is the acid-base reaction. This is the base, and this is the conjugate acid you just made. You know. Okay. Awesome. Product prediction. Any questions?
So what happened with HCl? What happened with HCl?
HCl and H2O is a strong acid. Yeah. Yeah. So we could say H2O here, but we want to make sure that all of that alkoxide is protonated, so we used a strong acid, all right, HCl. You could also say H2SO4. That works too. You could do HBr. You could do HI, hydroiodic acid. Couldn't do HF. I'll do HF, right? That's not a strong acid. All right. And I want to emphasize on these problems, you do not get points for drawing the mechanism in. That is superfluous. Don't draw the mechanism when they ask for a product. Don't draw the mechanism when all they ask for is a product. Okay?
Prediction questions?
For the product prediction questions, yeah, don't draw the mechanism. Do draw it on like a scrap paper, but all he's asking for is the product. Okay. We're going up here in complexity, okay? We're starting with this alkyne. Oh, we're still all right, starting with this alkyne. 1, 2, 3, 4, 5 carbon alkynes. All right, our first step is 1 equivalent of NaNH2. Second step is bromopropane. Third step is H2 over platinum. Oh, we're going fancy today. And our fourth step is Br2 over light. Move this a little closer. Oh, they're answering their own questions. Thank goodness. Okay. Great. Okay. It's okay if you don't have the answer right now, because we're going to go through it step by step together. But learn it, by Thursday. Okay. So 1 equivalent of NaNH2. The reason they mentioned Na1 equivalent is to throw you off, because all this is deprotonation of a terminal alkyne. It is the same as every deprotonation of a terminal alkyne today, tomorrow, and forever. Don't worry about the 1 equivalent thing. We're just flying the proton off of the end there. So you have this same funky trident isopropyl molecule guy with now a terminal alkyne. What is a terminal alkyne great for? SN2 reactions, elongating the carbon chain. All right. So we're going to SN2 this this propyl bromide, and we're going to add carbons to it. Now, I'm adding carbons. I'm going to number my carbons. No embarrassment, no shame. 1, 2, 3, 4, 5, 6. Right? One, 2, 3, 4, 5, 6. And here we had our isopropyl group. I didn't number that just because I knew to put the isopropyl group on. But if you want to do like A, B, it's good to have like a separate numbering system if you're going to do two different groups on the same molecule. Okay, so now we added a thing to that carbon chain, all right? One of the ways to elongate a carbon chain. All right, H2 and platinum. What does this do to an alkyne? You go all the way down, okay? We're no stopping, all right? No Lindlar's catalyst, no NH3. You go all the way down to an alkane, And the synthesis isn't over. So if you had to just fill in the fourth option, what's the one reaction you know how to do on an alkane? Br2 and light. Okay. And light is also denoted as HB sometimes. The reason they said that is the same reason they said one equivalent. It's to throw you off. You know the reactivity. Don't be thrown off, please. Okay. And then I'm going to do 2, 3, 4, 5, 6. So it will be 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. This is our alkane. All that for an alkane? I guess so. All right, Br2 and light. The most substituted spot on this alkane because it's Br2. So we're going to put it right there. Okay, so you get this bromoalkane, and after all of that synthesis, that's what we ended up with. Okay, not the most synthetically easy way to get to this product, surely, but you know it's what they did. So it's what you have to do. Yes.
Is there another Br added on a separate carbon?
No. Yeah. When you do Br2 and light, you want to look for your most substituted carbon.
Right.
This one is tertiary, and I only see secondary and primary carbons elsewhere. So I'm gonna just, yeah. You want to ask yourself, you're like, what are they testing you on when they show that Br2 and light? They're testing you on you knowing that Br2 and light puts a bromine on the most substituted carbon. Okay, so just look for the most substituted carbon, put it there, one bromine on the carbon. Okay, so this is our final product of that reaction. A very dramatic synthesis of this molecule, but a synthesis nonetheless. Okay, let's do another product prediction. Apparently, the reason they use bromine is because the other halogens are more expensive. Right.
The reason that's to do with how selective bromine was in comparison to chlorine. And chlorine is too electronegative and iodine is too large.
And plus, bromine has some weaker selectivity than chlorine.
Yeah, but in general, I mean, whenever you throw in a haloalkane, typically we're going to draw like bromoalkanes. Those haloalkanes could be bromochlorine, bromoiodine. Yeah, you are right. Do use bromine when it comes to doing Br2 and light or NBS or HBr and ROR, but there's no reason for it to be bromine when it comes to doing the haloalkane part, but it is still used. Okay, let's get a little organometallic here. Okay, so I'm starting with this alkene. Draw the product of those reactions.
On the exam, are we only going to be required to write the final product or
Each intermediate. Yeah.
each intermediate?
Yeah. So these are intermediates because they're stable, sort of middle guys along the way.
Right. Would we have to know how to mechanize them?
No.
Okay.
That's the great thing about product prediction. You don't need to draw a new mechanism. I often do like to draw a mechanism when I'm unsure of what the product of a step might be,
Yeah.
but that's it's equivalent to like putting 1 + 1 into your calculator on a physics test when you're unsure if it's 2. You know it's 2, but you just want to check. Draw the mechanism on scratch paper. Don't draw it on the test because that's not the question they're asking you. They're only asking you for the intermediate.
Does it make a difference, like, what, whether the things are on the top or the bottom of the arrow?
Good question. I mean, yeah, for our purposes, no. Sometimes you have the reactant on the top and the solvent on the bottom, but that's a preference. As long as you have a 1, 2, 3, 4 thing, you just do 1 step, 2 step, 3 step, 4 step, that sort of thing.
Right.
Okay, so I'm going to draw this out. We have an alkene, and right here I see a radical reaction because I have ROOR. Okay, HBr and ROR puts a bromine on the antimarconic opposition. Okay, so it's just like hydroboration of hydrobromination of an alkene, except it is anti-marconic. Right, so we're going to put our H here and our Br here. You don't need to show the H. I'm just doing that. Just to show you that that's what we added across the double bond in the first step. Okay, so 2 equivalents of lithium. All right, maybe we're getting organometallic. Okay, so that's the only time I've ever seen that asked for. And indeed, that would be, make sure you don't lose carbons. This is why I count my carbons. Okay, so 2 times of that. All right, we use 2 equivalents of lithium, so we're going to get 2 of these. Why? Because we're about to form the organocupric, and they're using copper iodide for that. Okay, so we have this copper, lithium, and okay, and you need to do it. This is an easier way to do it. Why? Because you'll have to draw this whole bulky group out twice if you want to do it the way I did before, where I did like copper and then the 2 groups actually flying off it. Draw it this way. It's just simpler. But remember, only one of them adds in, okay? Because there's only one spot for it to add in. Okay, so this is a vinylic haloalkene, okay? Vinylic haloalkene. That's the perfect substrate for a Gilman reagent, okay? At this point, I'm going to count carbons because I'm confused already. So 1, 2, 3, 4, and I'll call this one cat, or you call it dog if you want. Okay, and then this is A, B. Okay, so carbon number 4 is going to add carbon B. Okay, so I'm going to do A, B, and then we have carbon 4. That's carbon number 4. What is it bound to here? It's bound to carbon number 3, which is bound to cat. So that's a methyl group, and that is a methyl group. Okay, so that should be your product. I'm going to double check this to make sure I'm not faking you guys out in any way.
Where did the cupric lithium go? What did it react with?
Yeah, it forms like this, like byproduct. It doesn't. I mean, this is so the main organic product occurs when you do. Now I'm showing the mechanism here, but that's not, it's not part of your answer necessarily. It forms a salt in solution somewhere. I don't know how to write that salt, but do know how to write it because, that could be like show the extra product kind of thing. Okay, yeah, so that's the product. Notice that this is a chiral center. They like to emphasize chiral centers in your textbook for some reason. I do not know why, but to me, you might as well draw it this way because there's no chirality, there's no stereoselectivity here that we did at all. Okay. Now, let's put it all together and do our favorite kind of organic chemistry problem. And that's a synthesis. Okay.
I'll be right back.
Right. So in synthesis problems, you're given a starting material and you're given a product, and you're asked to draw the reaction arrows. Well, not the reaction arrows. The reagents necessary to complete that transformation. Okay. Synthesis. It is so called because you're synthesizing a new molecule from another molecule, right? So let's do a real easy one. All right, here I'm just demonstrating what a synthesis problem is. All right, if we wanted to go from cyclopentene to bromocyclopentene, what reagent do we need? Yes, exactly. NBS, N-bromosuccinimide adds a bromine to the allylic position, which is here or here. And since this is not a asymmetrical molecule, it's the same product no matter where you add it, thankfully. So here you fill in as your answer NBS on the top and light on the bottom. Okay, very simple one-step synthesis. I'm just sort of illustrating like this is the kind of question you're going to get. You've already gotten them probably maybe on exam 2. But this, these are the ones where you bring out a lot of reactions. Okay. And there's also multiple ways to do many of these syntheses. Synthesize, I don't know. Syntheses, yes. Thank you. Okay, so let's go from ethane to 1-butanol. Now, no mechanism required, no intermediates required. Simply draw me the reagents needed. I'm going to add one more thing to this. I'm going to say use any carbon source. All right, I specify that because you're going to need, obviously you're going to need something else. Actually, you don't really need another carbon source. But if you want to throw in another reactant without producing it first, I'm allowing you to do that. Hopefully, no. All right, in the meantime, I'm going to take a picture of this and does anyone here have access to the group chat for your class?
Yeah.
Okay.
But what's that? I don't think I have it.
Okay. If anyone does, I just want to send this synthesis like cheat sheet thing that I passed around here. I want to add it to that group chat just so everyone has it. Okay. I'm doing airdrop right now. Whoever wants to take the airdrop and send it to the group chat, just raise your hand and tell me what your phone is called.
I took my person.
Okay. You took a picture?
Yeah.
Okay, awesome. Could you send it?
Yeah.
All right, I just airdropped it to Judy's iPhone. So Judy, whoever you are, you just got it. Oh, and Naomi too. All right, so there's my Oh, did you get the handout I gave? Okay.
There's one here, I think.
One there? Okay, yeah, you can take that one.
Thank you.
See, it's right.
Okay, yeah. What did you do?
All right, do you want me to start backwards or forward?
whichever way you solved it.
Okay, so I did it backwards. So I started from there, and then I did HCl and water in that step. And then I had a 4-carbon chain with an oxygen and negative charge at the bottom. I did the last attached to carbon number 4.
Mhm.
And then before that, using in that step to get that, I had an epoxide. And then, so epoxide, and then before that was 1, 2, so a 2-carbon chain with MgBr. And then before that, I used Mg and ether from a methyl attached to a Br. So methyl Br. And then I did HuBr2 on top.
Okay, awesome. Okay, one thing you might have missed here is you just need an ethyl. So
Oh yeah, so I wrote. I don't know why I wrote.
That's okay. It's okay. Yeah, that's the answer. But let's go through each step. I like the way you did it. Do it backwards. It's called retrosynthetic analysis for a reason. It turns out that was actually like invented at a certain point. Retrosynthetic analysis. They used to just do synthetic analysis until someone figured out you could do it backwards. So great. This is an alcohol. All right. You really only know like one way to make alcohols, which is the opening epoxides. No, you actually know many ways to make alcohols, right? You could hydrate an alkene. You can hydrate an alkyne. Well, then you have a ketone. Really, just hydrating an alkene is your way. But this alcohol is many carbons long, okay? And if you want to make a terminal alcohol with many carbons long, you're going to want to use epoxide opening, okay? One of your options. Another option, you could have done anti-Markovnikov hydroboration of an alkene on a terminal alkene. That's another option. That would also work. But this is a great place to start because it gives us this 4-carbon long molecule. And you'll look, you see your product, you see your reactant. Here I have 1, 2 carbons. And here I have 1, 2, 3, 4. Okay? So really the easiest thing is just to add 3 and 4 at the same time using another 2-carbon molecule. Okay. So your first step going back is perfect. It's realizing that this H doesn't come from nowhere. It needs to come from an acidic workup. Okay? And that acidic workup could be HCl, it could be H2SO4, it could be HBr, any strong acid, and H2O. Get a lot of protons around. There you have this. That is the result of an epoxide opening. So you have this. Grignards and organolithiums open epoxides. That's the one that does it. That opens oxyrane, this simple epoxide. And then how do you make a Grignard? Well, you already know. That's magnesium and ether solvent. And then you have this bromo alkane. And how do you make a bromo alkane? You do Br2 and light. Okay, so another way to do this without plopping oxyrane in is to start from here. Okay, so you have Br2 on ethane here. You have Br on ethane, and if he had not said to use any additional carbon source, you could actually still do the synthesis. What I would do is I would see this as an E2 substrate. Okay, remember E2, SN1, SN2, E1, E2. E2 substrates are all around you. Okay, and they're still quite synthetically useful. So here I would do an E2 reaction using NaOH. Let's use terpetoxide to make sure it's E2. And that would give me this guy. Okay, so from here you actually know how to turn this into the epoxide using MCPBA, okay? So then, all you got to do is MCPBA it, and you have this epoxide. Okay, so that's synthesizing everything on your own. You don't have to do that. That's just like an extra sort of thing to do. If they do allow you to throw an epoxide in, that's great. But they did teach you the MCPBA thing, so be ready to whip that out if you want to. Okay. That's the synthesis. That's how I would do it. We're going to go over time, by the way. Hopefully my YouTube live doesn't cut out, but we did start a little bit late, so I'll go like 10 minutes over. So we have time for like one more problem in this session. Okay. and then I'll sort of open the floor and allow you guys to come ask questions if you have them, like special burning desires for answers. Okay. So okay, this is a good one to end on. It's a little involved. There's a few steps actually, but you can do it. And if you can't, that's fine too, because we'll go through it. All right. What are the reagents necessary to make this transition happen? Just write down the answer, and I'll go through the answer myself. So we're starting with ethene, 2 carbon long alkene, the simplest alkene you know how to draw, and then butene. Okay, that's a 4 carbon long, so but and then ene to show it's an alkene, and it is 1 butene because the alkene starts on the 1 carbon. Right? Synthesize it. No. Oh, yeah, I should actually specify no external carbon sources. Okay. So I'm going to now show how we do this. Okay. So right off the bat, I'm going to number my carbons on the left and the right. All right. Here I have 1, 2 carbons, and on the right I have 1, 2, 3, 4 carbons. So we're going to be forming a carbon-carbon bond in this synthesis, which means we're going to have to use either terminal alkyne, or organometallic reagent, and there's one more way you know how to form a carbon-carbon bond that is not an alkyne or an organometallic reagent. That is the cyanide anion for an SN2 reaction. But you don't really have to use those often because once you have a cyanide, you don't really know what to do with it at this point. You'll learn in Orgo 2, but they're not even that useful even in Orgo 2. Okay, so anyway, we're making a carbon-carbon bond. Probably gonna have to determine an alkyne, but like let's see how we get there. Okay, so my first step is to make a terminal alkyne. Okay, so I take my ethene and I'm going to add Br2. Okay, and then that makes this guy Br. And oh yeah, Br and Br. All right, let's show our intermediates here. Okay, I'm going forward, by the way, in this reaction. You could also go backwards, but I kind of just want to go forwards today. That's how I'm feeling. But I would always recommend going backwards. It works that way too. Really, if you know the synthesis in your head, you can go forwards. If you're not confident, then you should be confident that going backwards always works. Okay, I'm just going forwards because I already know the answer. Hate to pull the curtain on the wizard, but I know the answer, so that's why I'm going forward. Okay, go backwards. That's the better way to do it. But okay, so Br2. What are we going to do to make this an alkyne? Eliminate. So I'm going to use Na and H2, so we don't get any sort of substitution because Na and H2 is only a base, and we're going to eliminate. So here we have our alkyne. Okay, now I'm going to use one equivalent of Na NH2. Okay, well, okay. So first I'm going to eliminate. Then I'm going to do an acid workup to make my alkyne. And my acid workup is literally just going to be H2O. And then I'm going to eliminate again. And here I am actually going to specify one equivalent because it is very important that we only get one of these sides.
Would it be a swipe up any NH2 three equivalents and this NH2 three straight
No. Think about it. Okay, so we're now doing one equivalent of Na and H2, dot, dot, negative charge. Okay, the reason we can't just go write Na and H2 is because there's nothing to remove here. There's nothing to eliminate. So if you did Na and H2, I mean, is this acidic? No. Okay.
I did the in the second step we just do any NH2 three equivalents.
Yeah, okay, so you could get a terminal alkyne that way, but you can't stop that reaction from deprotonating both sides. I prefer to do it this way. You know that when you have a alkyne like this, you add one equivalent of Na and H2, and then only one side gets deprotonated. So if you want to, I like to do it this way. Yeah, if you did deprotonate this, or deprotonate this on both sides, you would get a di-terminal alkyne. So you would get this, like a dialkynide. That's why I'm going to do my acid workup first.
It's just like anything which is the second language, you have that three equivalents to just maybe one side having the other.
Okay, I mean, you can go with that. If your professor mentioned it at any point, then go with that. I sometimes organic chemistry as a second language says things that the professor doesn't say. I like to do it this way just because I'm like super duper confident in my answer right now that this works. But yeah, do it that way if you want. Right, three equivalents of Na and H2, you would get a terminal, an alkynide ion from this. Okay, because two of the removals would be to make your two double bonds, and then one of the removal would be to remove another proton to make your alkynide ion. I like to do it this way just because to me it makes more sense to have my alkyne first and then deprotonate one side. All right, same thing. Okay, very good question though. Now we have our alkynide, and the alkynide can attack a haloalkane, and it can make the product that we want after just one reduction step. But the haloalkane I need is something like this, and the problem tells me I have no other carbon source. So what am I going to do? I'm just going to turn this into a haloalkane using HBr. And you can do that because you have unlimited molecules here. Just make your reagent out of your substrate and then connect that with that. And the product of that reaction is this. Okay, so you have your alkyne. I'm going to number my carbons. All right, and 1, 2, 3, 4. Okay, so I have I'm almost there. This looks a lot like my product. One more step. We just need to use one of those reducing agents that stops the reduction at an alkene. And that is either Lindlar's catalyst or liquid ammonia and sodium metal. So I'll say Lindlar's.
So it wouldn't matter here just because it's terminal, right?
Exactly. So here it does not matter when it's internal. It does matter because then you'll have the cis trans isomerism in the product. Okay. So here we have 1, 2, 3. 3 lines between 4 carbons. That's a product. Okay. And I mean, the world is your oyster from there, you know? Just take a look at that synthetic toolbox and imagine what you can do with this. Yes?
So we did the HBr, then what about the alkyne with the negative alkyne anion?
You need the alkyne anion to attack that. So that's what elongates your carbon chain. Whenever you have a carbon-carbon bond, you should think organometallic or alkyne. Okay? Those are the ways you know to make carbon-carbon bonds. Okay? And that's what was so great about the Grignard reagent, is that it was like the first way they figured out how to make
You have a few
carbon-carbon.
questions.
Okay, questions.
If Li is written as a reagent but not specified two equivalents of Li, do we assume that Li is in excess?
Yes.
Okay.
I would do that because why else would they show it to you?
Can you react NaNH2 with a terminal alkene or only a terminal alkyne?
Only a terminal alkyne. It's because the sp orbital on this, so like let's say you have this alkene, you have a proton here and a proton here, and this is an sp2 hybridized atom. So these are two sp2 hybridized orbitals right here that are holding your hydrogens. So those are the ones that would hold your negative charge, right? The p orbital here is busy doing resonance in this double bond, but you have two sp2 orbitals that are sigma bonded to your protons, okay? So it turns out that the sp2 orbital has a little bit less s character because you're taking two p orbitals and one s orbital to form it versus, well, let's do an alkyne, right? It's linear versus this, which has, since it's sp, which has just one p orbital and just one s orbital. So that's 50% p character, or s character. Yeah, 50% s and 50% p because it's sp. Okay, so 50% s is the one that we're emphasizing here because that is a smaller orbital. And if you think about like the reason for electronegativity, right? As you go right across the periodic table, you increase electronegativity because you decrease the size, right? So those atoms want more electrons in part because they are smaller and also heavier. So they hold their electrons in tighter. So we're looking for something that is holding electrons in tighter to be more electronegative. sp orbital is more electronegative than sp2 orbital because it is holding its electron tighter because it looks more like this little p orbital than it does like that big. No, it looks more like that little s orbital than it does like that big p orbital. Yeah, I wish they had named this hourglass and ball instead because then I wouldn't keep mistaking them. Okay, do you have another question?
Yeah, and then somebody said I made an alkene with Br and a Greenguard reagent and reacted the two and got the same answer. Would that be acceptable, or do you think that takes similar steps?
You're showing this.
Yeah, that's what I did. I made a finger and a post. We are two overlight, then we are two together.
Yep, that's great.
Okay.
Yeah, that works. Okay, so let's do the alternate answer for this.
You didn't do it that way because you said no other carbons of source.
So I used to say the same thing. The same alkene together.
Yeah. So you made this alkane first.
No. I did
Like that?
no. I did the alkene with the Br2 overlight. And I will react one side and that turning down.
I don't know if that's considered using.
I can't really tell what you're saying. I'm sorry.
Oh,
You did an alkene with what?
I did the alkene with Br2 overlight,
Yes.
and that was one thing by itself, right?
Okay.
And then I did the alkene and turned that into the Greenguard. Now I reacted both together.
Okay. Well, this you wouldn't react with Br2 over light
No, why not?
because this is an alkene. You only know how to do HBr over ROOR or NBS over light for an alkene. You would use HBr for this. That gives you this. So HBr, no light. And then I mean, you could use this. I mean, you could make this a Grignard reagent, just using magnesium. And then you could do this with MCPBA. But then you would be stuck with this, just an alcohol.
I was thinking about trying to do that.
Yeah, I just, there's a way to do this actually if you had Orgo2 reactions, but you can't, you just can't get, I mean, this is the way I would do it, okay? I see a double bond in the product, I see a double bond in the reactants, I'm thinking terminal alkyne. This other way though, this also works. So,
Was that considered using new carbon chain since I made it in the product?
Ooh, okay. Very good question. So one thing you cannot do is just an SN2 reaction with the Grignard reagent. It doesn't work. You can't. Yeah. So you can't take energy Br and Br and do that. Yeah, I would love if that was the case. I mean, it looks very logical, but This is forbidden. Okay, no go.
Explosion or a bomb?
Maybe I don't even want to find out. And it's forbidden. So they just don't teach you that. Good point to note. Safe. You do not do an SN2 with Grignard. Okay, don't do an SN2 with Grignard. Only do epoxide opening with Grignard. Okay, that's the only reaction you know with the Grignard. All right, Gilman, you could do vinyl halide. The only thing you know with Grignard is epoxide opening, which you really can't use to solve this problem. Go with the Alkyne for this one. I mean, that's what I would do. Right? That's just my personal preference. Okay, so two things I just want to close with that are like my cardinal advice before your exam and before any finals you have in other courses this week. One, when you're studying, you practice what you're going to do on test day. If that means coming up with mechanisms that you've memorized from nothing, do that to study, okay? Do not read the mechanism from the textbook to study. You draw out the mechanism from your memory to study. That is studying, and that's active studying. You're actively recalling it, bringing it forth, which is what you're going to have to do on Thursday, okay? More important than that even is to get good sleep. You are going to be getting problems wrong if you get poor sleep the night before. Doesn't matter how much you've studied, you should get very good sleep that night before. I know it'll be hard, but try to really like tucker yourself out the day before and just get good sleep, okay? That's the most important. Don't study up late the night before. It's not gonna help you. All right, so I'm gonna open the floor now for anyone who wants to come up and ask me questions, and I'm gonna end the YouTube live stream. But thank you all so much for coming. I don't know where the sign-in sheet is, but you all have to sign that with your name and your EMPL ID if you're here in person. So please do that. All right, and good luck to everyone.
Thank you.
You'll all be great. There's not a problem that you cannot solve, right?
Somebody asked what you saved because they want to rewatch it.
Yeah. I think there's an option on YouTube for me to save this. All right, bye everyone. Thank you so much for watching. All right, and good luck. Good luck to everyone who came to this live stream. You'll all do great. It'll be hard, but get good night sleep the night before. Bye bye.